This is the Milky Way, our home, a spiral-shaped galaxy where our solar system is located. The Milky Way is composed of approximately 400 billion stars separated from each other by trillions of kilometers. If we observe the sky in an area with little light, clouds, and pollution, it is possible to see a whitish band composed of millions of stars. This band of stars is the visible part of the Milky Way. Thanks to its whitish appearance, it was named the Milky Way or Via Lactea by the ancient Greeks. Our galaxy has a diameter of 100,000 light-years and is composed of arms made up of billions of young stars, gas, and dust, which, because they are rotating, give the Milky Way its spiral shape. In addition to the disk, the galaxy structure is composed of the bulge and the halo. The bulge is a circular area located in the center of the galaxy and is mainly formed by older stars with a reddish color. The halo, a circular structure that surrounds the entire galaxy, is formed by scattered stars in very old star clusters. And it is precisely here in the Milky Way that we can observe some of the most incredible cosmic phenomena in the universe. And in today's video, we're going to travel to some of these places. To get our bearings, we'll explore the most accurate and complete map of the Milky Way, produced by the incredible Gaia mission, a probe that, in addition to mapping the position and movement of nearby stars, also detected some exoplanets and stellar black holes, something incredible even for current technology. Continuing our journey, we will visit the stars closest to the Sun, such as Proxima Centauri, GJ 699, and the Beaver Multiple Star System. These stars show us that we don't need to go very far to find incredible objects. After this, we will visit two promising exoplanets in our galaxy, TOI 733b and K21b. Two incredible worlds that are possibly covered by global oceans, and one of them possesses a molecule in its atmosphere that could change everything we know about exoplanets and biosignature signals. And to conclude our journey, we will explore one of the most extreme objects in the universe, neutron stars, specifically J0952, a fascinating star that is very close to collapsing, which will cause an extremely energetic explosion and the formation of a black hole. If this happens soon, it will be the first time we see the formation of a black hole in real time. My name is Pedro. Get ready to embark with me on this incredible journey through the Milky Way. Music. Taking a picture of the entire Milky Way might seem like a simple idea, but it's not. The problem is that we're inside the galaxy, trapped in one of its spiral arms, with no way to step back and see the complete picture. And as you can imagine, sending a spacecraft equipped with a camera to the edge of the galaxy today is impossible. The distance is simply absurd. Our galaxy is over 100,000 light-years in diameter. It would take billions of years to reach a point where we could finally take a picture of the entire Milky Way. Capturing the Milky Way in a single image today is impossible. Astronomers use a different strategy. They map it piece by piece. Using powerful telescopes, they observe millions of stars and celestial objects and then assemble the most accurate portrait of our galaxy. And that's exactly what you're seeing now. This is the most accurate map of the Milky Way ever made. It was built from an impressive 3 trillion observations collected from 2 billion celestial objects over 11 years. This is the masterpiece of the European Space Agency's Gaia mission. For the past 10 years, Gaia has been tirelessly scanning the sky, and the result is simply breathtaking, offering both a frontal and lateral view of our galaxy in incredible detail. But the telescope has done much more than just map stars. It has revealed secrets of the Milky Way that we never even imagined. Gaia may not be as famous as Hubble or the James Webb Space Telescope, but in the world of astrophysics, it has caused a real stir in our understanding of the galaxy. Its discoveries are reshaping everything we know about the structure, composition, and evolution of the Milky Way. The Gaia Space Telescope was built based on the mission and resources, which was a pioneer in space astrometry. Hipparcos mapped about 120,000 stars, something monumental at the time. But Gaia took everything to a completely different level, aiming to catalog almost 1 billion stars, about 0.5% of the galaxy's stellar population. Applause, launched in December 2013 and costing about $1 billion, Gaia traveled to Lagrange point L2, about 1.5 million kilometers from Earth, just like the James Webb Telescope. But what really differentiates the Gaia's remarkable achievement lies in the absurd precision of its measurements. It can determine the position of a star with such extreme accuracy that it's like measuring the width of a human hair from 1,000 km away. Gaia is more than just a space telescope. It's a true masterpiece of engineering, designed to map the Milky Way with unprecedented accuracy. But how does it achieve this feat? Well, at the heart of Gaia are two identical telescopes separated by an angle of 106.5 degrees. This unique design allows each star to be observed twice, while the spacecraft slowly rotates, capturing the light from different objects. A sophisticated system of mirrors directs this light to Gaia's camera, the most powerful ever launched into space, equipped with 106 CCDs and almost 1 billion pixels. CCD is nothing more than a charge-coupled device, a light-sensitive integrated circuit that captures images by converting photons into electrons. They are present in various devices, from cell phones and digital cameras to the James Webb Space Telescope. Music. As stars enter Gaia's field of view, they first pass through astrometric CCDs, which measure their exact positions and track even the smallest movements over time. By observing a star multiple times, Gaia detects its parallax, that small shift in position caused by the Earth's movement, and thus calculates its distance with impressive precision. Then, the stars pass through photometric CCDs, which use prisms to split their light into different wavelengths. By analyzing this, Gaia determines the brightness, temperature, size, and even the chemical composition of each star. Finally, some stars reach the radial velocity spectrometer, which separates their light into a spectrum, revealing whether they are approaching or moving away from us thanks to the Doppler effect. Unlike traditional telescopes that observe one target at a time, Gaia rotates continuously, sweeping its instruments across the sky. This ensures that each star is observed multiple times from different angles, creating an incredibly detailed 3D map of our galaxy. And the numbers are simply insane. Gaia scans more than 2 million stars per hour, generating over 50 gigabytes of data every single day. The most incredible thing about Gaia is that its repeated observations aren't just static snapshots of the Milky Way. They reveal its movement in stunning detail. Each star has its own trajectory across the sky, known as its proper motion. By tracking these movements, we can go back in time or even move forward, watching the entire galaxy come alive as stars shift, rotate, and evolve. Even constellations that appear fixed in the sky slowly deform over thousands of years. But the movement of stars isn't limited to their own paths. It also reflects the journey of our sun through the Milky Way. Applause. When scientists analyze the average movement of stars within 1,000 parsecs of sun, Gaia reveals the grand orbit of our solar system around the galaxy and improves upon it even further. By combining Gaia's precise measurements of distances and radial velocities with proper motion data, it's possible to create incredible 3D visualizations of how stars actually move through space. Take a look, for example, at these 74,000 nearby stars within an area of 100 parsecs from the Sun. Some move toward the center. Others are flung toward the edges of the galaxy. Most follow stable circular orbits in the galactic plane, appearing purple, but some deviate, going above and below the disk, shining in yellow and red. In this way, Gaia has given us the clearest and most spectacular view of our galaxy, completely transforming what we thought we knew about it. Music. Over the past 10 years, their discoveries have proven that the Milky Way is far more complex than we imagined. For a long time, astronomers believed that our galaxy had only 2 main spiral arms and a few smaller ones. But Gaia data tells a different story, showing that there are more than 2 arms, although they are more tenuous and intricate than older models predicted. The view of the Milky Way from above offers a mesmerizing spectacle. A bright golden core at the center, like a cosmic lighthouse, with its elegant spiral arms extending outwards, forming an almost perfect swirl. The profile view of the galaxy is simply striking. Against an absolute black background, we see a thin, dark brown disk stretching across the image, curving slightly along its length. That's right. Thanks to Gaia, we now know that this disk is not perfectly flat. It is warped. And what's more, this warping is not fixed. It moves over time, like a spinning top that wobbles as it turns. And here comes the real mystery. This wobble is happening faster than expected, suggesting that there are hidden forces shaping our galaxy in ways we don't yet fully understand. One of the most intriguing discoveries made by the Gaia mission is the Headcliff Wave, a gigantic undulating structure gas that extends an impressive 9,000 light-years across our galaxy. This enormous wave makes up about 40% of the Orion Arm, the same spiral arm where our solar system is located, and lies between 400 and 5,000 light-years away from us. Before the detailed 3D mapping done by Gaia, this structure was practically invisible, appearing only as isolated star-forming regions. Now we know that the Redcliffe Wave is the largest continuous gaseous structure in the Milky Way, containing about 3 million times the mass of the Sun in gas. Furthermore, it plays a fundamental role in star formation in our galactic neighborhood. The most incredible thing is that our Sun is only 500 light-years away at its closest point, as if it were literally surfing on this wave. In fact, models indicate that the Sun crossed this structure about 13 million years ago and will continue to cross it in the future. But what exactly caused this gigantic ripple in the galaxy? Applause. The truth is, scientists still don't know for sure. One hypothesis is that a collision with some massive object, like a dwarf galaxy, disturbed the gas, forming this wavy pattern. But of course, more data from Gaia will be needed to unravel this cosmic mystery. Moreover, Gaia also revealed clues that a galactic collision may have been the trigger for the formation of our solar system, and it doesn't stop there. The mission also helped to better understand the impact of the Sagittarius Onan galaxy, a small galaxy that has been orbiting and colliding with the Milky Way for billions of years. Music. Discovered in the 1990s, the Sagittarius Onan galaxy is tiny compared to the Milky Way, containing only a few tens of millions of stars, while our galaxy has hundreds of billions. As the powerful gravity of the Milky Way pulled Sagittarius closer, and this dwarf galaxy began to cross the disk of our galaxy, a process that has already happened at least 3 times, approximately 6, 2, and 1 billion years ago. With each collision, the Milky Way ripped more stars from Sagittarius, making it smaller and smaller. And eventually, Sagittarius will be completely absorbed by our galaxy. But even though it's small, the dwarf galaxy had a gigantic impact on the Milky Way. A 2020 study revealed that each collision generated waves of star formation, like when you throw a stone into water and see the ripples spreading. These waves compress the gas and dust, creating the perfect conditions for the birth of stars. The most incredible part is that one of these collisions happened about 4.7 billion years ago, exactly when the Sun and the solar system began to form. And a 2019 study showed that before these collisions, star formation in the Milky Way was slowing down. Until about 5 billion years ago, everything changed. Star formation suddenly skyrocketed. In fact, almost half of all the stars that exist today in the thin disk of the Milky Way, where most stars are located, were born at that time. This suggests that without the collisions with Sagittarius, our galaxy would be much fainter and have far fewer stars. Thanks to Gaia's precise data, we now have a detailed history of how our galaxy evolved, revealing that even small cosmic encounters can shape gigantic structures in the universe. And Gaia's influence on astronomy continues. Far beyond mapping the Milky Way, its data has led to groundbreaking discoveries in virtually every field, from tracking asteroids in our solar system to locating hidden black holes, and even detecting exoplanets in distant star systems. The mission has already mapped the orbits of more than 150 asteroids, giving us a super clear view of the dynamics of our own system. And this vibrant image shows exactly the paths of these asteroids, from the inner regions to the distant Trojan asteroids orbiting near Jupiter. The colors in the image represent different regions of our solar system. The yellow circle represents the Sun, blue indicates the inner solar system, green marks the asteroid belt between Mars and Jupiter, and red highlights Jupiter's Trojan asteroids. One of the most fascinating discoveries of the Gaia mission was the identification of possible moons around approximately 350 asteroids, classifying them as binary asteroids. These pairs were observed wobbling in their trajectories across the sky. Normally, a solitary asteroid travels in a straight line, but when Gaia noticed the deviations, it revealed the presence of companion satellites orbiting the main asteroid. The extremely precise measurements from Gaia's sky mapper also led to the discovery of dormant black holes. These are called dormant black holes, which emit virtually no radiation. Unlike active black holes that pull in matter and shine with high-energy radiation, these remain invisible to traditional methods because they are not consuming surrounding matter. Gaia identified these hidden black holes by detecting anomalous movements in the trajectories of stars near these gravitational monsters, a clear sign that a massive, invisible object is pulling on these stars. So far, 3 of these black holes have been confirmed: Gaia BH1, BH2, and BH3. Among them, Gaia BH3 stands out. It has the widest orbit and is the largest stellar origin black hole ever found in our galaxy, with a mass equivalent to 33 times our Sun. It is located in the constellation Aquila, just 2,000 light-years from Earth. Recently, Gaia also revealed 2 fascinating celestial objects: Gaia 4b, a super-Jupiter-type exoplanet located 244 light-years away, and Gaia 5b, a brown dwarf situated 134 light-years from Earth. This discovery is especially exciting because it is the first time a planet has been discovered solely using Gaia's ability to detect the gravitational interaction between planets and stars. Both objects are extreme. Gaia 4b is almost 12 times the mass of Jupiter, making it one of the largest planets ever found. Orbits a low-mass star. Meanwhile, Gaia 5b, a very large anachronistic star, also orbits a low-mass star, a combination that scientists consider extremely rare. These discoveries demonstrate how Gaia is becoming increasingly powerful in the search for and study of exoplanets and strange objects in the cosmos. Even with all that the telescope has already revealed, much of our galaxy still remains a mystery. Although Gaia has already completed its observations, the journey of discovery is far from over, but 2 major data releases are on the way, one in 2026 and another in 2030. These future updates will further enhance the already impressive map created by Gaia, offering more precise details about the structure, movements, and evolution of the Milky Way. As scientists continue to explore this veritable treasure trove of data, our view of the galaxy will become increasingly clear, rich, and complete, bringing us closer than ever to truly understanding this immense stellar mass we call home. Unfortunately, after more than 10 years of revealing the mysteries of the Milky Way, the Gaia mission was recently deactivated on March 27, 2025. On that date, the European Space Agency sent the probe its last signal, ordering it to deactivate its communication systems. But in any case, its work was done. Thanks to this incredible telescope, we have the most detailed map of the Milky Way. And in addition, we still have 2 future data releases that could bring even more unimaginable discoveries. A fitting end for one of the most important telescopes in history. Music. We are already used to hearing about the absurd distances of a universe. A simple example is the Alpha Centauri system, home to the closest star to the Sun, April 2nd light-years away. This means that if by some miracle, humanity ever finds a way to travel at the speed of light, it would take 4 years to reach Proxima Centauri, a red dwarf star and the closest to the Alpha Centauri system. To give you an idea of this distance, NASA's Parker Solar Probe is the fastest object ever created by humans, traveling at 635,000 kilometers per hour while orbiting the Sun. Even at that absurd speed, the probe would take more than 7,000 years to reach the Alpha Centauri system. Remember that this is the closest star to us, apart from the Sun, of course. But despite these impressive numbers, it's absolutely nothing compared to the vastness of the cosmos. This is only our galactic neighborhood. And here is home to some incredible stars, like the red dwarf GJ 699, the extremely bright Sirius, and the curious Beaver system with its 6 stars. Within a radius of 50 light-years around our planetary system, we only have a small glimpse of the immensity of the universe. But I guarantee our cosmic neighborhood can surprise you. Music. After a long journey, we will arrive at our first stop, a small red dwarf called GJ 699, also known as Barnard's Star. Besides being extremely close, it is also notable for its incredible speed of movement across the sky. This is due not only to its proximity to us, but also to its large proper motion, moving at an incredible 10.3 arcseconds per year. Barnard star is approaching the solar system at speeds slightly above 100 kilometers per sun and could become the closest star to the sun in about 10,000 years. When this happens, the distance between Barnard's star and our sun will be only 3.8 light years. But the red dwarf is so faint that it will not be visible even at this small distance, being observable only through telescopes. The star's mass is only 17% that of the sun, and its radius is 6 times smaller than that of our star. Like all red dwarfs, Barnard's star is quite cool, with a surface temperature of, in quotes, only 2,900 degrees Celsius. With these characteristics in mind, it is not surprising that the object's luminosity is 2,300 times less than that of our star. In 2018, the results of a 20-year observation of the star's proper motion were published, which may provide evidence of the presence of an exoplanet nearby. Calculations show it to be a cool super-Earth with a mass at least 3.2 times that of Earth. The planet, named GJ699b, is located about 0.4 astronomical units from the center of the system and takes 233 days to complete a full orbit around its parent star. Unfortunately, the exoplanet follows an orbit that does not lie between Earth and its star. Therefore, it is impossible to perform transit and spectral analyses of the object. However, mathematical modeling can provide us with some information about what this world is like. Because Barnard's star is very faint, the planet receives 50 times less energy than Earth receives from the sun. Therefore, the temperature on the surface of the celestial body is extremely low, around minus 168 degrees Celsius. However, it cannot be ruled out that tidal effects or radioactive decay may have released enough energy inside the planet to form a subsurface ocean. If so, in the depths of this ocean, a potential life form would have had enough time to gradually develop, since among known stars, Barnard's star appears to be one of the oldest. According to estimates, its age is over 10 billion years, which is only a fraction of the life expectancy of a red dwarf. Because it is located very close and is moving in a favorable direction, Barnard's star is one of the highest priority objects for a potential interstellar flight, being only farther away than the 3 stars of the Alpha Centauri system. Time will tell if spacecraft launched from Earth will ever reach it. Meanwhile, on the other side of the sun, opposite the position of the red dwarf, lies the brightest star in the night sky, Sirius, which is 8.6 light years from our planet. From Earth, the star appears to be a single light source, but closer observation reveals that it is not a single object, but a binary star. The 2 components of the system are currently at their maximum distance from each other, about 30 astronomical units. The main star, also called Sirius A, is a bright bluish-white star, with twice the mass and a diameter 70% larger than that of the Sun, and reaches an incredible temperature of almost 10,000 degrees Celsius. Because of this, Sirius A emits 25 times more energy than our Sun. The second object, known as Sirius B, is barely visible compared to its bright companion. This is a white dwarf with a radius of about 6,000 kilometers and a mass very close to that of the Sun. Like all stars of this type, its surface temperature is extremely high, reaching 25,000 degrees Celsius. However, due to its small size, this white dwarf is about 10,000 times less bright than its stellar companion.